Alright, here's the final stretch of chapter 11. There's not much left. Last time we looked at data of temperature and pressure, and we were able to plot the 1 over T versus the natural log of P. Retrieved a linear equation by doing the natural log, applying the natural log, and we were able to use the slope and this equation here to calculate the heat of fusion for this particular liquid, which I believe is ether. So you don't have to do that if you can just use 2 points, right? Instead of using all of those to you get better data this way. But you can just single out 2 points and use a 2-point equation, and I'm more likely to ask that particular process for an exam. And so this is the equation. It's called the 2-point form, and you can calculate then, in this case I'm providing you with the delta H of fusion. This is for water now. 20.7 kilojoules per mole, as we know already, is the delta H of vaporization, the energy required to boil 1 mole of water at the boiling point, 100 degrees. But they're asking for the vapor pressure of water at 25 degrees. All right, so and they give you the normal boiling point and the delta H of vaporization. So we have everything, plus we know what R is. We have everything but P2, and we're given the 2 temperatures. Of course, temperature 1 is going to be the 373, which is boiling. So take note that I added 273, that's Kelvin, equals the degrees Celsius plus 273. You probably remember that from first semester, hopefully. Degrees C plus, it was 273.15. That's how I got the 373 Kelvin. And so we know at this, we know the pressure, the vapor pressure there is equal to the external pressure, so that's 760 torr. And then the other temperature is equal to, it's 25 plus 273, so it is, it's 298 K. What we don't know is the pressure of that, and so that's what X becomes, and so you just simply plug all that in, and you get the natural log of X over P1 equals negative 40.7 kilojoules per mole. R, which will be provided to you, is 8.314 joules per mole times Kelvin, and then 1 over 298 K minus 1 over 373 K. You plug all this into a calculator and you end up with negative 3.30, which of course is still equal to the natural log of X over, and we do know this is 760 torr, regular pressure, TORR, right? And so how do we get rid of the natural log? We take the inverse natural log, which means that e to the negative 3.30 is going to be equal to X over 760 torr. And you may want to play around with your calculator to see if you can find the inverse natural log. There's the inverse log and the inverse natural log. It should just be pretty easy to find on your calculator. Here's that clean, and then the second part is here all written out, and when you calculate that, you get a value of 0. So e to the negative 3.30 is that, and then you multiply by that, of course, by 760 torr, and you end up with 28 torr. Obviously you're going to have a much lower pressure to boil that at room temperature. So that is basically the end of boiling, heat of vaporization, except for this this little tidbit here. You've heard of supercritical fluids. They can be used in industry to extract chemicals, and so we already understand that if you're starting to boil something in a confined container, that pressure will build up, and then you probably will blow up the container. But if you have a really sturdy container that can withstand the pressure, you are going to end up with what is called a supercritical fluid, which has a property that's somewhat in between a liquid and a gas. It's fairly unique. It's not its own phase, but it is. And you can see here looking inside of the container here, where it looks like it's a cross section of a tube. You see the liquid, and that white line divides the liquid and the gas, and as you increase heat, you can see that starting to boil until it all looks like it's a homogeneous mixture. And so that's just vocabulary wise. It'll become important later when we look at phase diagrams. All right. So in addition to boiling, there's obviously different kind of processes that we can go through when we apply heat to substances, right? Not everything is a liquid or a gas. We also have solids. And so you can have a solid that melts at a certain temperature, but it can be colder, right? In the winter, you can have ice that's colder than freezing temperature, because sometimes it's in the negative ranges. So there's actually a value similar to the specific heat of a liquid. There's a specific heat of a solid. So the energy required to warm up ice, and which is similar to the energy required, but has a different value. And we're going to look at all of those. But the other factor where we are melting is called the heat of fusion here in blue on this particular. And so the energy to melt something is, of course, a lot lower than the energy to evaporate something, because when you're just melting, you're just loosening up the water molecules to make them mobile. When you're boiling, you're breaking that hydrogen bond and sending those molecules off to opposite ends of the world, right? Anyway, so that's just here demonstrated by the bars. This is not just true for water. It is true for here. The other examples are rubbing alcohol, acetone, and diethyl ether. And diethyl ether has, and you can see a couple of things here. You can see that the intermolecular forces decrease here nicely from going from water to rubbing alcohol. Rubbing alcohol has also an OH group, and it's got a very small nonpolar carbon-carbon group, so it's highly polar, has a pretty high boiling point. But the intermolecular forces are pretty high, and then so the heat of fusion is going to be pretty high. And it decreases for acetone, which is less polar, and then diethyl ether, which is even less polar. But the main point here is that melting for any substance is going to be a much lower energy process. So let's look at the heat of fusion a little bit on a diagram here, right? So this is water. Again, it's a different section of the heating curve, and so here is the liquid that we're just warming up. So we would use specific heat here, right? Remember earlier we had 4.18 joules per degree Celsius per gram that we're using to determine any energy input or release between 0 degrees and 100 degrees of this liquid. And then we have the melting point. So this is when you are already at the melting point, which is 0 degrees Celsius for water, and you are simply going through the process of melting it, whether it's a mole or 400 grams or whatever it is. The quantity does matter. And so this stretch here can take longer for larger mass. Of course, there's more heat input here. I mentioned briefly already, so this here is just warming up ice, and so it gets an entire different value that we need to calculate. So the heat of fusion actually is 6.02 kilojoules per mole compared to the heat of vaporization, which was 40.7 kilojoules per mole. Of course, quite a bit different. All right, so let's look at all the different parts that I could ask you about on an exam or in the active homework set. So there's not This is an entire heating curve from going from negative 25 degrees to 125 degrees Celsius. So if this is water, and of course I can ask you for anything other than water, it would look different, but it would have the same zigzag features, just it would just have different temperatures. But so we're going from 25 degrees to 125 degrees, and it's going to be ice, and it's going to be exactly 1 mole. So 1 mole is then also equal to 18 grams. So whenever we are using heat of fusion, when we have the gram, we will use 18. Whenever we use mole, we just use mole. And so we're going through each of these segments here, and so kind of ignore that for now. Those are already the numbers that are determined for 1 mole of water. Okay, and so segment 1 is heating 18 grams of water to the melting point. And you should recognize that just by looking at it, that 1 here, when you change the temperature, is warming up. Then, of course, the 2 areas that are flat, you are then doing something, either heat of fusion or heat of vaporization. And so segment 2 is just melting. You're melting the piece of ice. Segment 4 is of course boiling, and then when we undergo the change in temperature again here in segment 3, that is just warming up water. So specific heat of the liquid will be used, and then you can actually take steam. It can be hotter than 100 degrees Celsius. You can heat it to 150 or 600 degrees if you wish, and that's the heat, also specific heat of steam. And so we're going to go through each segment slide by slide, using going from negative 25 to 125. Okay, so just as a summary, and I will provide you with these numbers here. Those are the different constants or values that we will be using, and they're not in order here. But if you start at negative 20 degrees and you have a piece of solid or ice, you're going to be using the specific heat of for a solid, which is 2.09 joules per gram per degree. That's heating ice from from negative 25 to the melting point, which is 0 degrees Celsius. And then the second part will be melting. Then of course you're going to at 0 degrees melt, and that would be the heat of fusion. So we will be using this value here, 6.02 kilojoules per mole, for melting between 0 and then to 0, and then until it's all completely melted. And once it's melted and everything is a liquid, then you are going to use the specific heat, which is 2, and then you're going to be boiling, which is, that's number 3 here, and then segment 4 is boiling, and once you've turned all of the liquid into steam, you are going to be heating the steam from 100 to 125. So those are the constants that you will be using, and you'll have to figure this out yourself and practice that. But so segment 1 is we're going to take 1 mole of ice at negative 25 and melt it. So if you fish out the correct constant or factor here, and you look at the units, you have joules per gram per degree Celsius, you know what to do, right? Because you need to cancel the units, and we're after Q, which is heat or energy, which is measured in joules. And if you know that, just looking at the factor, you should understand that you need to multiply by grams. And if they want to give you 1 mole, you need to make the connection and know that there are 18 grams per mole of water. So you multiply by the mass of that, that's 1 mole, 18 grams, which cancels the grams. And then you also need to multiply by the change in temperature. And so we are going from negative 25 to 0, so that would be 25. That is 25 degrees. And when you multiply 18 by 2.09, and then by 25, you get 941 joules. This is just, if you divide that by 1,000, this would be a kilojoule, just warming up the specific heat of the solid. So next we're going to be melting. So now we use the heat of fusion, And so just knowing what heat diffusion is will help you fishing out that constant. And then looking at the units, we have kilojoules per mole, and we want to do this for 1 mole. The temperature doesn't change, so all we have to do is multiply that by 1. So 1 times 6.0 kilojoules per mole is 6.02 kilojoules per mole. That would be the second part here. All right, so you add the two together, and we have part 1 and part 2 together. Now, part 3 is now we are completely melted. Now we're going to change the temperature again and heat it, so we will use the specific heat. Specific heat has units times temperature, and we are given 0 to 100, so the change in temperature is 100 degrees. The specific heat is 4.18, and again, a mole in grams is 18 for water. Our grams cancels and degrees cancels, on our units are in joules, 7,520, change to kilojoules, 7.52, and that was this part right here, segment 3, when we have the liquid and we are warming that up. Now that we've melted it all, the next process is to boil, and for that we use the heat of vaporization. And that is, of course, 40.7 kilojoules per mole. Since we're doing this for exactly 1 mole, it is that value. So this is here where the curve is flat. And the final part is we are heating steam by 25 degrees from 100 and going to 125. I have a bunch of problems like this in active. All right? Okay, so we have the final part then is the heat of steam. It is almost the same as heating the solid, not quite, but it's 2.01 joules per gram per degree. So again, we don't have a mole, so we go back to our grams. The change in temperature is 25 degrees. And so we end up with 0.904 kilojoules. And so there's just above here they have calculated each of these. That's exactly what we're doing here, right? And then you can add it all up for the total energy required. And so those are all positive value, because everything there you stick energy in and it's absorbed by the water, and that's should have a positive value. Now on active, and I snipped this from active, on active you may not have such a detailed information. All you get to see is a zigzag line, and you will be required to tell me where is it boiling, where is it evaporating, what's the temperature, the boiling temperature, and all that. So part 1, you need to recognize that so right here where the curve is flat, which is about 80 degrees, that must be the melting point. And so this is where we apply the delta H of fusion for whatever liquid or solid, wherever substance that is. And it looks like it boils at about 120 degrees Celsius. Again, that's where it's flat, and so this is where boiling is. Well, that's where the boiling point is, right? And all of this is assuming that the external pressure is constant. And so the other 2 sections here, 3 sections here, of course, heating the solid, heating the liquid, and heating steam. And so I may simply ask you, but I have to provide you with the constants, of course, the delta H of fusion, the delta H of vaporization, and specific heat of whichever phase the particular substance is in. But I could ask you calculate the heat required for cooling. Okay, so that would be negative if we took, let's say this is, I honestly have no idea what this is, some sort of oil. I'll just call this oil. Let's say you have an oil at 140 degrees Celsius, and you're going to just cool it down to 100 degrees. So you start here and you go to 100, which means you will go through 3 different calculations in this point. So you're going to have to calculate the energy released in this section here, which is cooling the steam from 140 to 120. That's step 1. And when it's at 100 degrees, then, sorry, it's when it's at 120 degrees, at its boiling point, of course, when we're cooling, we're not boiling, we're condensing, it's going to condense, and so that's simply the opposite value with a negative value. Let's say if it was water, it would be 40.7, so it would be negative 40.7 for condensation. That would be the second part, and the third part is then cooling the liquid, and that's the specific heat of that liquid, of course the negative value again, from 120 to 100 degrees as specified here. All right, and so this is Active has a whole bunch of good stuff for you to practice on that. So that keep that in mind. That'll be on the exam, and we will do some of this in the lab as well. Finally, we can look at all these processes in a so-called phase diagram. This is a phase diagram for water, for example. It has all three phases here and different temperatures and pressures. So you can actually look at that and determine, if we didn't know, just based on that, if this was like an unknown substance, and I ask you what's the boiling point, what's the melting point of this substance, and you'd go for the 1 atm, which is normal temperature and pressure, and you'd just kind of go across. All right, and so when you hit the this curve here, which is the line between solid and liquid, then that would be the fusion curve, and that means that's where melting and freezing occurs. So depending on which way you're going, right? You're melting going. This is melting, and this is freezing. Okay, and so we know here this is 0 degrees, and then you keep going where you hit the curve between the gas and the liquid, and that's where your boiling point is. So you can and you should also understand is obviously if we lower the pressure, then so this is here ambient pressure, but if you lower it, you can actually lower, and that's why this is going down, right? This curve here, down, because you can actually boil water at below actually freezing point if you wanted to, if you decrease the pressure enough, right? And that's there's also something called the triple point. This is where all three phases meet, and so you can determine that also by simply looking at the pressure and temperature. Looks like the triple point here. It's super hard for me and I don't to tell, but if this was 0, maybe would be 680 torr, and then this is almost like 0, like 1 degree Celsius. That's where the triple point is. This is where all three phases meet. And we mentioned the supercritical fluid already, which is when we have, and that's why we don't have a line in this area for water, because it can be a supercritical fluid. Alright, so this is an example of a phase diagram. You need to be able to tell me if I give you a temperature and a pressure, is it a liquid at that, or is it a solid, or if I'm increasing heat or decreasing heat, are we melting, are we boiling, what is the phase transition that we're in? And so, for example, if I ask you, well, this is again for water, but you can kind of tell here what's happening. As you heat at 1 atm, and if you start at low temperature here, let's say you start at negative 25, as you heat, keeping the constant, the pressure constant, you will go to here about 0, you will go to melting, and then here you go to boiling. You can also do this at a different temperature here, or a pressure, like at 0.0 atm. If you start at that same temperature at negative 25, you are actually going to go through the triple point. That's what the triple point is, and at 0.01. But let's just use this as an example as you go through it. So you're going to completely skip the liquid. You will go straight, and that's called sublimation. You will go straight from at 0.06 atm. You will and you might have noticed that in the freezer this can happen. You can have sublimation. Your ice can end up, unless you have a self-defrosting freezer or something like that. So it goes straight. It will go it will sublime. It will go from solid straight to gas at 0.06 atm. One last example. What state transition occurs when a sample of carbon dioxide at -60 Celsius and 10 atm is warmed to 30 degrees Celsius and 10 atm? So the first thing we notice is that the pressure here does not change. So this is 72 and this is 5.1. So again, it's kind of hard to tell where it is. They give you the red arrow, but if you had to guess, it'll be right around there. This is your 10. This is the line you're looking for. And now we're looking at -60. So that's here. So we start as a solid. So it's asking for the phase transitions, right? So you first of all, as you warm this up, you're going to go from solid to liquid. So you're going to melt. So at about, it looks like -56.7, it's going to melt. And then you heat it some more all the way to 30 degrees, which is over here. And then you're going to start, and I'm not giving you a great scale here, but maybe that's 10 degrees. I'm totally guessing here. But you're going to go through melting as well, and then this will, you've melted already here. You're going to go through boiling. So this carbon dioxide will also boil. Again, this also sublimes, right? Dry ice is what carbon dioxide is. We know it at room temperature at 1 atm, and it will not go into a liquid. It will just go to a gas. And so that's what's shown here, that you don't go through melting, you go through, this is sublimation here. So this right here is all sublimation. Well, this is pretty much the end of the chapter. And if you have the book, here are a few suggestions for you to study and work the problems. If you don't have it, OpenStax has a whole bunch of problems to work, as well as practice problems on active and practice problems and homework on active. All right, peace out. See you in chapter 13.